Hello everyone. Thank you for attending this talk. I am Maulik Bhatt, a PhD student at University of Illinois Urbana-Champaign. Today I'll be presenting our recent work on autonomous multi-agent racing using constrained potential dynamic games. This is my recent work with my collaborators Yixuan and Professor Negar. As we know, autonomous racing is very famous these days because of its wide applicability in various interactive motion planning scenarios. Autonomous racing is a highly challenging task as it requires multiple non-linear agents to plan their motion in real time while operating at their limits. Agents has to plan their motion while keeping other agents' strategies in mind and generate behaviors such as blocking other agents, pushing other agents against the wall, or overtaking other agents. Such highly competitive and interactive behaviors are very difficult for even humans to generate, as we can see in this video. Autonomously generating such behaviors and generating trajectories which are highly competitive is a very difficult task, and it requires a highly computational efficiency and real-time applicability. There has been various approaches on autonomous racing. One of the initial approaches in autonomous racing was a very simple idea where we use a model predictive controller to move along the racetrack as fast as possible while treating other agents as obstacles. This is a very simple approach and it fails to generate competitive behaviors. There has been some learning-based planners as well. These learning-based planners mainly focus on path planning aspect of autonomous racing and forget the interactive nature of the racing. As we know, dynamic games and game theory provides a strong mathematical formulation to deal with such highly interactive scenario. As game theory inherits it inherently uh, tackles the interactive nature of the problem, and it consider other agent strategies and find the best possible strategies for all the agents. There has been various recent works in game theory which shows that formulating the problem as a converting the problem of autonomous racing as a game and seeking Nash equilibria generates in highly interactive behaviors and generates competitive trajectories and generates behaviors such as blocking and overtaking. One of the recent work in autonomous racing was by Wang in 21, which showed that seeking Nash equilibria using iterated based response resulted in highly efficient trajectories. Taking motivation from all this previous work, we modeled the racing problem as a dynamic game for our work. We assume that each agent has their own dynamics and they have their own cost functions. Here, X represents the state, F represents the dynamics, and U represents the control. Subscripts are used to denote time steps, and superscripts are used to denote the agent indexes. And J is the objective for each agent. These objectives are the ones which captures agents' behaviors. Furthermore, apart from all this, each agent has to satisfy some safety constraints, such as not going out of the racetrack, not colliding with other agents, and finishing the race. All these constraints are captured by some safety constraints, which are denoted by G. In our problem, we aim to seek generalized Nash equilibria of the underlying game, which essentially means that you have to find a set of strategies which ultimately determines your control inputs such that each agent's objective is minimized and no agent can deviate from Nash equilibria and obtain better results. And while doing all this, each agent has to satisfy constraints such as dynamic constraints and safety constraints. However, solving for generalized Nash equilibria is a very difficult problem as it requires solving coupled constraint optimal control problems. There has been various recent approaches to solve this problem, ranging from iterative LQR to uh, uh, dynamic programming based method to various other methods. In our work, our key idea is that the generalized Nash equilibria of the resulting game can be found by solving a single constraint optimal control problem instead of having to solve coupled constraint optimal control problems. We show that under certain cost structures, autonomous racing problem can be cast as a dynamic potential game. By this reformulation, we can convert the underlying constrained optimal control problems, which are coupled, into a single constraint optimal control problem. And solving a single constraint optimal control problem is a much simpler task, and therefore it is very efficient to solve. Now I'll explain a little more about constraint potential dynamic games. Constraint potential dynamic games, as I uh, suggested earlier, in our original game, the problem is of n-coupled constraint optimal control problems. And if the conditions of constraint potential dynamic games are satisfied, then that problem can be reformulated as a single agent constraint optimal control problem. And you can associate potential function P with this problem. In our previous work, we have shown that by minimizing this potential function subject to constraints, we can obtain the original Nash equilibria of the system. Now, with this in mind, let's get back to our racing problem. We need to formulate our objective of each agent such that the game is a potential game while it captures all the intricacies of racing. We, taking motivation from previous work, we formulate our racing objective as the following term, which consists of two terms, where the first term essentially corresponds to maximizing the progress along the racetrack, while the second term essentially captures all the interactive nature of the racing, which includes blocking behavior, overtaking behavior. Mm. And alpha is an hyperparameter. As we can see here, we are trying to minimize the distance between both the agents, which may mean that if an agent is behind the other agent, then it will try to overtake the agent and stay close to it and generate blocking behaviors. And if it's already ahead of the other agent, it will try to block the other agent by preventing overtaking behavior. And here alpha is the hyperparameter which we decide empirically to find the best results. With this cost in mind, we generate highly interactive racing behaviors such as overtaking and then blocking and then winning the race ultimately. Now I'll come to our main results, which shows that under the cost structures which I mentioned previously, the racing problem becomes a constant potential dynamic game with a potential function which is shown as here. And with this, you just need to minimize this potential to find the Nash equilibria of the original game. And since this is a single agent optimal control problem, you can use any generic optimizer to solve this problem. In particular, we use a do MPC, which uses IPOP to solve this optimization problem in a model predictive fashion. Now, coming back to our results. With this algorithm, we show that our algorithm is very fast and we compare it against a baseline method from previous work, which uses iterated best response. We show that, as I have shown in this, our ego agent is the one which uses our algorithm, is able to win against baseline by pushing it against the wall and ultimately overtaking and winning the race. We found out that rapid is very fast to solve and its average solve time is about 4 times faster and it wins the race more frequently against the baseline. And with this in mind, we wanted to check the scalability of our algorithm. And we found out that our algorithm scales to multiple agents in a much better way than the baseline. As the number of agents increases, our algorithm is solving the game much faster than the baseline. And therefore, we can efficiently capture interaction with more number of agents. Now we wanted to examine our agent's performance on real-time hardware. And for that, since the baseline was very slow and we are not able to implement it in real time, we compare our method against a reactive MPC, which aims to move along the racetrack as fast as possible while treating the opponent as an obstacle. So, with this opponent, our agent uses our game theoretic algorithm, and we found out that in most of the in almost all the races, our agent is able to overtake and generate blocking behaviors. If it started late, it was overtaking the agent, and if it started before the opponent, then it would always generate blocking behaviors and prevent the other agent to overtake and win the race ultimately. Furthermore, mm, we did some hardware experiments with three agents where we show that our algorithm is always superior to the opponents. As we can see in this figure, uh, our agent started first, but it had lesser speed limit and it was still able to win against the opponent by generating blocking behaviors, as we can see in this experiment. We performed few other experiments, as we'll see following. Yeah, so in the second experiment, as you can see, our agent started our agent started second, and it was still able to overtake the other agents and then again generate blocking behaviors and then win the race ultimately. So even in our hardware experiments, we observed that our algorithm was very superior and was winning the race uh, most of the time. And in conclusion, I would like to say that we address the problem of path planning for multi-agent autonomous racing. And we address this problem using game theory. And our key idea was that we designed a cost structure under which the racing problem becomes a constrained potential dynamic game that can be solved tractably and efficiently. In future, we would like to compute the hyperparameters using theoretical results instead of empirical results, and we would like to explore more complicated cost functions to capture various racing scenarios. Thank you. Feel free to reach out to me if you have any more questions.